Okay, welcome back. This is now 15.6 surface integrals. And the setup for us in this section is going to be two versions of kind of everything we do, the function, the version in terms of x and y, and then the versions in terms of u's and v's, right? So you get two formulas for the price of one in every section. Right, so the idea here is you're integrating over a surface. There, clearly. So here's maybe some weird sort of surface that we have in space. And the way we generally do it, if it's given as a function of x and y, we have kind of chopped this region up into a bunch of little areas. And for the regular surface integral, so the double integral over this region of ds, this formula giving us the surface area, what we were doing was kind of adding up a bunch of little surface area increments, right? We would kind of take that point and look at the size of the tangent plane to the surface at that point here, and we would get that by doing a cross product, and then we would kind of sum up over the surface all these little tangent planes, and that would be this thing here. Okay, so the little elements here we had as change in t sub I or change in s sub I. Okay, and yeah, those things would be the magnitude of these cross products of these vectors, which we could write in terms of the partial derivatives of the function that represents the surface. Okay. All right. So what we want to do now is maybe attach a value to this little element. Okay, and that could be anything you want. It could be a temperature value. It could be I don't know, a slippery value, so it's really slippery here as opposed to over here. It could be a density value, obviously, for for figuring out mass and things like that. It could be anything you can imagine. It's just an incredible thing, right? So that's what we're going to do. We're going to tack onto this thing kind of an extra piece and maybe call that delta whatever. I'll call it delta h sub I, where now we're attaching some other function, so not the surface function, but some other function. So the surface function we call z and equals g of xy, right? So this f is some other function in terms of x, y, and z, and at every point on the surface, you'll get some output of some real number, right? Whatever it represents, I don't know. So then it would be times the change in t sub I, and we would want to go through over the surface and add all these up in an integral. And so you would have the sum of these change at h sub i's, and then we'd want to take the limit of that thing. And that's what we're going to be working with in this section, right? So it's going to be the double integral over the surface of whatever function you're doing, maybe a temperature function, like I said. So the double integral over the surface of this thing. So there'll be two forms for it. First, the surface integral of f over the surface given by, sorry, we get over the surface given by the function in terms of x and y. Okay, so in that case, the working definition for our integral will be this guy, our f of x, y, z, and then times the square root of, this would give us the area of the little tangent planes, right? And then dA, so that's our working definition there. The other version then, part B, where instead of this z equals g of xy, we have this R of UV. Okay, in that case, instead of using this, you have to use the literal cross product element, okay, in the formula. So it's a double integral over, and in this case, it's some region in the UV plane, and then you have f of, and you're going to have to reparameterize x, y, and z in terms of u's and v's. Okay. And then we have the, the cross product thing. A lot of fun, huh? And then dA. I mean, obviously, once you get a handle on this kind of junk, you just hand it off to a computer, but it's an incredible thing. I mean, you could build these things to do anything you want. Okay, so anyways, let's maybe look at some examples now from the book of actually doing some of these. So one application is finding mass. So find the mass of the surface lamina. The surface is given by 2x plus 3y plus 6z equals 12. And we're in only the first octant. And our rho function for the density is given by x squared plus y squared. Okay, so what? Well, I need a couple things, right? If you go back and look at our integral, we need some partial derivatives. I need to figure out what this region is. So I guess I have pretty much everything else. One thing to note here, maybe I shouldn't have wrote this in terms of f and I shouldn't have put both f's. These guys should be g's, right? So if you allow me to just could really feel the coffee kicking in at this point. But these are g's, not f's. Sorry about that. They're different, right? This is some added factor, right, which is different than the surface. Okay. Hopefully that didn't confuse the heck out of you. Okay. So anyways, let's identify. This is the f of x from that formula. This thing up here is the g formula, okay? And in order to use this thing, I'm going to have to rewrite it in terms of z equals something, right? So that's probably one of the drawbacks of using this kind of integral as opposed to a vector valued integral, right? With the u's and v's. Okay, so I have to solve this for z. So I have 2x plus 3y plus 6z is 12, right? And then I move everything over. I get 6z is 12 minus 2x minus 3y, divide both sides by 6, and z is 12 minus 2x minus 3y all over, what did I say, 6. Okay, so that's our g function, right? Z equals g of x comma y and the formula. If I can find wherever it is. Yeah, so that would be the surface formula. Okay, so it has to be written in this format. All right. We're going to need the region to integrate over. So this thing is some plane. It's one of those ones where you can kind of pick off the intercepts and draw if you wished. But let's put it in the xy plane. And so in those cases, z would be 0, and you would end up with let's see. So 12 minus 2x minus 3y all over 6 is 0. Okay, so this would be 2 minus x over 3 minus y over 2 is 0. I want to solve for y. So y over 2 equals 2 minus x over 3 multiplied by 2. So y is 4 minus 2x over 3. Okay. So 1, 2, 3, 4. What am I doing? I'm going down 2 and then over 3. 1, 2, 3. And then this will be 1, 2, 3. So it should go like that. And that'll be my region. Okay. All right. So I'll be integrating in this orientation. This is x, this is y. Alrighty then. I need the partial derivatives. Gx is g with respect to x is going to be negative 2, 6. So negative 1/3. G with respect to y, negative 3y over 6, so negative 1/2. Okay, and then I think we're ready to dump everything into the integral. So I have the double integral over this region here of my f of xyz function, which is this density function here. So I just plug that in, x squared plus y squared. And then times the square root of these guys squared plus 1. So 1/9 plus 1/4 plus 1. And then I'll go in the orientation dy dx. Okay. So my integral is going from where to where? So curve to curve. So y equals 0 to y equals 4 minus 2x over 3. Okay. And then the Riemann man is going from 0 to 6. Okay. And then the rest I'll just leave to you. You should be able to integrate that. Okay, let's look at one where the surface is given in terms of u's and v's. Okay, so this will be number 15. No, not number 15. Yes, number 15. All right. So this time, the function, I don't know what it represents. It's just purely math type thing. And then our surface is given in terms of u's and v's. So that's going to be 2 cosine u, comma 2 sine u, comma v. Okay. They also give you restrictions on u's and v's. So u is going from 0 to pi over 2, and then v is going from 0 to 1. Okay, so you can imagine it's probably like half a cylinder going from 0 to 1 on the z-axis. Or maybe not even half a cylinder, it's a quarter of a cylinder because of this. Okay, so what do you need? You need a lot of stuff, right? You need the cross product here. I need to figure out the region I'm integrating over. I need to reparameterize the f function in terms of u's and v's. Okay. All righty then. So I don't know. Let's get the cross product stuff first, right? So r with respect to u, and then r with respect to v. So with respect to u, I'm going to get negative 2 sine u, and then 2 cosine u, and then the derivative of v is just 1. We have ijk. And then down here, with respect to v, 0, 0, 1. Oh, 0, 0, yeah, 1. This should be 0, sorry. With respect to u. Yeah. Okay. Then I need the cross product of that, and then get the magnitude of it. But first, the cross product, cover those guys up. First component is 2 cosine u. Second component, negative 2 sine u, so positive 2 sine u. And then lastly, these 0, 0, so just 0, 0 minus 0. Then I need the magnitude of that, so that's going to be the square root of the component squared. So 4 cosine squared plus 4 sine squared, you factor out the 4, and then you get 4 times cosine squared plus sine squared, which is just 1. And then the square root of 4, of course, is just 2. Okay. I can start building my integral. The region and the UV plane is going from 0 to pi over 2, and then the v direction 0 to 1. So my Riemann man is going in this direction. So my the traditional ordering is going to be dv, then du. So I need to go dv and then du. I need to reparameterize this thing in terms of u's and v's. So it's just going to be x plus y is 2 cosine u plus 2 sine u. I have to smush that in. Sorry. Okay. Okay, so there's no room. All right, so it's double integral of 2 cosine u plus 2 sine u. That's f of x, y in terms of u's and v's. And then times this magnitude of the cross product, which is 2. And then the ordering I'm doing based off this picture, v first and then u. So I go dv and then du. So going curve to curve, and the region I'm integrating over is a box. So curve v equals 0 to v equals 1. And then the Riemann-Man is running from 0 to pi over 2. Okay? Okay, and then that's the integral. And again, I'll just leave it to you. I'm sure you can figure that out on your own. The answer is 8, if you're wondering. And so maybe pause the video and get the answer on your own. Or let's see what the other answer was, just in case you're super interested. Ugh, the other answer was, for the previous problem, did that number 11. The answer was 3/64. All right, great stuff. So when you're dealing with these surfaces in space, it's not a bad idea to get some sort of orientation, and we can accomplish this with normal vectors. We'll want to know the inside and the outside, because some of the applications that we work with, that will be important to know. So section 2, orientation. And so you have basically 2 normal vectors for a surface. There's going to be this normal vector going in this direction, and then a normal vector going in this other direction, right? So one or the other, and you can designate one to be the outside of the surface and the other one to be the inside of the surface. Okay, so let's figure out formulas for these normal vectors. Right. So the first form is when you have the surface given in terms of x's and y's. Right. So in that case, our normal vector will be the gradient of this g function. I'm going to have to rewrite this in order to pull this off. Okay, so I'll rewrite this by subtracting this formula, this function, or whatever it is, onto the other side. So I'll have z minus g of xy equals 0, and then I'll call this thing big G of x, y, z. Okay. And then for my normal vector, I'm going to be taking the gradient of g and dividing out by the magnitude of that gradient. Okay. And that does it. So why, why is that thing normal to the surface? Well, if you think about, if we think about maybe doing a parameterization of this g function in terms of t and then taking its derivative. So note, if we have g of x of t, comma y of t, comma z of t, then I could take the derivative of g with respect to t, and then from the chain rule, that's just going to be the partial of x with respect, or sorry, the partial of g with respect to x times the derivative of x with respect to t, plus the partial of g with respect to y times the derivative of y with respect to t, plus the partial of g with respect to z times the derivative of z with respect to t. And I know that this thing is equal to 0 from the way I've set it up, right? So basically, what is this thing? This thing is the gradient of g dotted with this dx, dt, dy thing. So some vector x prime of t y prime of t, z prime of t. Okay? So what this is saying is basically that the gradient vector is, if this is equal to 0, the gradient vector is perpendicular to what this thing is. It's basically just a tangent vector on the surface to the curve on the surface. So if this is my surface in 3 dimensions, maybe you have some r of x, y, z going over it. And what this x prime, y prime, z prime is a tangent vector on it, like this. And this formula, this dot product, says that this vector and this vector are perpendicular. Okay, so this gradient vector here would be orthogonal to this tangent vector, and that's true for any curve that you put on the surface, right? So the spiel is then it'll also be perpendicular to this curve, the tangent vector on that curve, and then over here, and then over here, and you can kind of think of these tangent vectors as spinning around and creating this tangent plane, and this gradient vector is always perpendicular to it. So that is ultimately the normal vector to the surface. And then to make it the unit normal vector, we just divide by the magnitude of the gradient. Okay, long story short. What the frick is that thing then in terms of what's going on here? Well, it's going to look kind of familiar. In particular, the numerator then is the partial derivatives of g. Here's our g function here. Okay, so the first component with respect to x, z will be 0, and you'll have g sub x. The second, negative, right? And then the second component with respect to y, z will be 0, and then the derivative of this with respect to y. And then the partial derivative of this whole thing with respect to z, so this will be 1 and this will be 0. Okay, so I'll have 1. And then downstairs, the magnitude of that thing is just the component squared, and then it's like, oh, that's familiar. That's really familiar, right? That's from that cross product when we would find tangent planes, the areas of tangent planes. So it turns out I can rewrite a lot of my integrals using this factor, okay? And it's going to have some nice cancellation cancellation sort of qualities to it. Okay, so we'll see that here coming up with flux. The other version then, part B, where I have a vector valued version, R of u comma v, that thing, the normal vector is going to be quite a lot like this, right? So if we think of this as sort of in reverse, the denominator is the kind of magnitude of the cross product of these vectors that we would have on the surface, right? So I don't want to go through this humongous derivation. I'm just going to kind of give you the formulas. The normal vector is going to be r cross r sub u cross r sub v all over its magnitude. Okay? And I hope you appreciate the fact that this thing, it looks an awful lot like the ingredients we used for our surface integrals over surfaces. Surface integral of f over some surface s, right? Or just finding surface area. It had those components in it. So anyways, there's two versions of these. One is just the negative of the other. So if you put a negative sign in front of all this jazz, you would get the other orientation, and ditto for this. Okay. Let's move into flux integrals, though. Okay. So we're not going to spend too much time on orientation. It's there. Okay, flux integrals. This is really, really neat. So much what we do in calculus just doesn't seem like it has too many applications, but this thing really seems like it has applications. And right, so what are we doing here? We have some sort of surface. I'm going to draw this on kind of like this. Okay, and it's given in your XYZ plane. So this could be a portion of a cylinder or something like that. And then you imagine in this XYZ space, not plane, you imagine in this XYZ space a vector field. Okay, and the vector field, in physics, they kind of want you to think of that as fluid flow. So it's like some fluid that you're immersed in. But I like to think of it in these days as kind of air, because we're worried about the pandemic and the spreading of disease and stuff like that. So what we want to do is, you can imagine air particles floating about, and we could describe the air particles with a vector field here. So maybe if the person is sitting right here and they're behind the mask, and they're coughing or whatever, the air particles are going in this direction, and those little arrows describe a vector field in space. And then they're going to hit the mask, and some of the guys are going to go through it, some aren't. But the more perpendicular the little arrows are to the mask, the more probable they are that they're going to go through the mask. So if you have an air particle that's kind of really going parallel to the mask, it's probably not going to go through it. It's just going to kind of bounce off, right? So I don't know, you have some particles maybe that are bouncing off and going this direction. And you can mathematically describe that movement, I assume, with some sort of vector field. Okay, so you have some vector field in space here. And what you're going to do is integrate over this surface and add up kind of the alignment between the vector field and the normal vectors on this surface. Okay, and you could describe the alignment using the dot product. So if you remember the dot product, what the heck was the dot product? So a dot product, like u dot v, was equal to the magnitude of u times the magnitude of v times the cosine of theta. So when these vectors are in alignment, that means this theta angle, which is the angle between the vectors, is going to be very close to 0. And then, think about the cosine function. The cosine function is at a maximum when it's at 0. Okay, so the dot product is kind of a measure of the alignment between two vectors. Okay, the bigger the value of the output of the dot product, the more these vectors are going in the same direction. So on this surface, you're going to have all these normal vectors, right? Pointing directly out of our mask. But then you can think of the air vectors, which represent the vector field, which we're using as the idea of a vector field. So, depending on how the person is breathing or coughing, these air vectors will kind of either be in alignment or out of alignment with the normal vectors. And you could add all of those up and get some sort of measure of how much of the coughiness is going through the mask, right? Isn't that awesome? You could do this with calculus 3. It blows my mind, right? So you have all these perpendicular vectors, and what we're going to do is integrate over this surface and add up all of these alignments. Right? That's how I intuitively think of it. You can go online and kind of get your own interpretation. Weird thing about teachers, sometimes I'll have to teach something that kind of fits it in your brain somewhere, but maybe it's not 100% accurate, and I hope I have not done that inadvertently. But okay, so what is this mathematically? What are we kind of doing mathematically? I'm adding up all of these little elements over this thing. I'm going to call them delta V's because they're kind of like volumes, right? So we'll have the area element, like maybe right here. And then on top of that, we're going to be multiplying in the dot product of the normal vector and the force field vector. So I would have some f sub I dotted with n sub I. And then I still have the tangent plane increment. So delta s sub I. Okay? So it's really the area of this times this thing here. Okay? And that's just going to, the bigger that number is, the more alignment you're going to have between the vectors, and that just means the airflow is going orthogonal to the mask, and in my opinion there's more probability that the air will go through the mask. Okay? And maybe then that would lead to questions about how porous should I make my mask. If it's solid metal, there's no air going through it at all, and stuff will just billow out the sides and maybe even curl around, and you would have to study those effects. Okay? So this, they study that kind of stuff at the CDC. I think one of my students got a job at the CDC optimizing masks right out of college. This is probably like 5 years ago, or maybe even 7 years ago. Okay, but anyways, right. So what we're going to call this, the sum of this thing is going to be flux. Okay, so the flux integral will be the limit of the sum of all these delta V elements, and basically it's just a surface integral. Okay, so you're adding up this new function, which is a dot product of the force field vectors and the normal vectors, okay, over the surface. And this is the flux integral. All righty then. We'll have, again, 2 versions of it. So the first version is when z, the surface, is given as a function of x and y. Okay, and in that case, we'll use our orientation formulas to rewrite n. Okay, and there's a nice cancellation that happens. So this will be the double integral over, in our working definition, some region R, and then we have the force field vector dotted with the normal vector, but the normal vector we can rewrite as negative g sub x, negative g sub y, comma 1, all over the square root of g sub x squared plus g sub y squared plus 1, and then times this ds element, which we write as a square root, and you see, oh my gosh, there's an awesome cancellation there, right? G squared y plus 1, and then dA. Okay, so that will turn into then sort of our working definition. F, the force field dotted with the gradient, negative gy 1 dA. Okay, so that's one version, and then the other version, when you're giving it something in terms of U's and V's, okay, surface and U and V, sorry, and parameters U and V. Our formula, is some vector valued equation in terms of U and V, and what will that look like, right? So I have then a double integral over some region in the UV plane of f, which will have to be reparameterized in terms of U's and V's. So x of U, comma V, comma y of U, comma V, comma z of U, comma V, and then dotted with our normal vector, but in this context, the normal vector is just a cross product all over the magnitude of the cross product times then the magnitude of the cross product dA. So those magnitudes will cross out, and we're just left with RU crossed RV, and then that's multiplied by this area element dA. Okay. Okay, so we want to actually set up one of these. We'll do the sort of the surface given in terms of x's and y's. This will be problem 25. Okay. All right, so we have this force field. It can represent anything you want: water, air. The videos I was watching last night, they say it's better to think of these force fields as some sort of liquid. Okay. The surface we're working with is z equals 1 minus x squared minus y squared, where z is greater than or equal to 0. So I need to figure out the region I'm integrating over. So what is this thing, basically? If you think in chapter 11 terms, it's a quadratic surface. So when z is 0, I get x squared plus y squared is equal to 1. And that's just a circle with radius 1. And then yz, when x is equal to 0, you get z equals 1 minus y squared, which is just an upside down shifted parabola. And then likewise for xz. Z has to be greater than 0, so you're only thinking this portion of it up here. So ultimately you get kind of this object or this surface that we're integrating over, okay? And the region R that the surface lives over is, is the XY plane of the circle in the XY plane, right? So it's just a circle, radius 1. Okay. All right. So I need to build my integral now. So I'm integrating over this region. I'm not going to get too carried away with the region yet, because I think we're going to have to some polar coordinates, right? So I have my force vector x, y, z, and then I'm dotting it with, what the heck am I dotting it with? The gradient of g. This isn't g though. Remember, we have to rewrite this to get our g function. So g of x, y, z is going to be equal to z plus x squared plus y squared minus 1, and that equals 0. Okay, so you need to kind of do that conversion before you can come down here and input your material. So with respect to x, it's 2x. With respect to the derivative with respect to y is 2y. The derivative with respect to z is 1. And then we have dA. Okay. All right, so let's go ahead and dot product that thing. So it's 2x squared plus 2y squared plus z, but we're going to rewrite z, right? Because we want all in terms of x, y. So you could use this expression to rewrite z as 1 minus x squared minus y squared, and then times dA. And then simplify that, and we get 2x squared minus x squared is x squared, likewise for y squared, and then plus 1 dA. And then we're going to convert that into polar coordinates. So I'm integrating over this region. So that's r equals 1. So going from r equals 0 to r equals 1. And then theta is varying from 0 to 2 pi. And then I replace all this stuff with r's and stuff. So x squared plus y squared is r squared. So I replace that thing with r squared, then plus 1. And then I can replace the area element with r d theta. And distribute the r, so r cubed plus r dr d theta. And I'll take this one home. Integral then r to the 4th over 4 plus r squared over 2 from 0 to 1, and then d theta. So plugging in 1, that's 1/4 plus 1/2. Okay, that's 3/4 d theta. Let's make sure 1/4 plus 1/2. So this is 2/4. So yeah, 3/4. Then that's 3/4 theta from 0 to 2 pi. And of course, that's just 6 pi over 4, which is 3 pi over 2 for our final answer. Okay, so powerful, powerful stuff. Hopefully my video helps. I don't know. It's there. There's a lot of stuff going on there. Okay, thanks for watching. See you next time.